Now I would like to invite our next speaker, Malar Chellasivalingam, who will be presenting her project, Mastery of Microchip Technology to Tackle Air Pollution. Welcome, Malar, and please share your screen. I can actually already see it.
Okay. Hello all, I am Malar, a PhD student in the engineering department. Today, I'm going to introduce my project to you all, which is the mastery of microchip technology to tackle air pollution. I'm supervised by Professor Ashwin Seshia for this project, who's also my PhD supervisor. And I thank CAPA for funding this project and giving me this platform to introduce my project to you all. So let me start with a historical overview. Shown here is the Nelson's column in London in the year 1952. During the December month of the year, it was a period of cold weather, and when combined with anticyclone and windless conditions, it formed a thick layer of smog all over the London city. People were asked to stay indoors, as we are doing now. Even then, the smog penetrated the indoor areas and reduced visibility. Within 5 days, 4,000 deaths were reported. Most of the deaths were caused by respiratory tract infections, which in turn were due to lung infections created by the smog. The UK government investigated this further, and then the Parliament passed the Clean Air Act in 1956, because of which the Nelson's column in the London city looks like this now. So, what are the main contributors of this smog? One of the main contributors of this smog is the particulate matter, which was the result of burning coal by that time. Even now, these particles exist because of emissions from industries, vehicle exhaust like the diesel engines, aircraft engines, smoke, and so on. If you see this is an image of a human hair under a microscope. This single strand of human hair is about 50 to 60 micron in diameter, and the particles are the particulate matter that I'm talking about are normally grouped as PM10 for particles less than 10 micrometer in diameter, PM2.5 for particles less than 2.5 micrometer in diameter, and ultrafine particles for particles less than 100 nanometer in diameter. In this project, I'm focused on the ultrafine particles, that is the particles which are less than 100 nanometer in diameter. And I'm using MEMS technology to detect the presence of these ultrafine particles. Currently, light-based commercial technologies are used for detecting the particles based on light scattering. When light falls on the particles, the light gets reflected back. Based on the reflected information, the size of the particle will be determined. But mostly, the current optical technologies are limited because of diffraction limit, and they cannot go beyond 300 nanometer sized particles. Because if they tend to go beyond the 300 nanometer sized particles, the size of the measurement instrument and the complexity of the instrument itself increases. So, over the past few years, research has been carried out to develop portable and chip scale sensors based on MEMS technology for detecting these particles. The MEMS sensor shown here combines the MEMS sensing element with the microfluidics, and shown here is a portable MEMS sensor comprising a silicon micro cantilever as the sensing element. And these are other MEMS sensors based on thermal transduction principle. And these have also been implemented in the form of an array, which is less than the size of a coin. And this one here is a portable MEMS prototype developed in our research group called as the MEMS impactor stage. A PCB board carrying the MEMS resonator attached to a chip carrier can be placed within this MEMS impactor stage. The particles can then be inertially impacted onto the MEMS resonators through the nozzle arrangement at the top. Previous work in our research group has focused on the square plate piezoelectric bulk acoustic MEMS resonator operating in its square extensional mode. The square extensional mode expands equally in all the 4 directions, with the red points being the sensitive points of the resonator. So if you note carefully, in all these MEMS sensors, the resonant frequency shifts based on the mass of the particles deposited on the resonators. This is very important because the current engine emissions or the air quality standards that have been set are mass-based. But We should note that this resonant frequency not only shifts based on the mass of particles deposited, but also due to fluctuations in ambient temperature and pressure. So in order to solve this problem, I propose using the coupled MEMS resonator as a solution. So what is the specialty of this coupled MEMS resonator? This simple mechanical beam coupler connecting the two MEMS resonators makes all the difference, which is nothing but this works based on vibration mode localization principle. In simple terms, we can model this coupled MEMS resonator system as a mass spring dashpot system. And if we assume symmetrical conditions, considering equal masses and equal spring constants, and the two masses being connected by a mechanical spring, the displacement of the two masses will be equal when a force is applied. In electrical terms, the amplitude of vibration sensed from these two resonators will be equal when a voltage is applied. So under symmetrical condition, vibration energy will be distributed equally between the two resonators. If we then try to create a disturbance or asymmetry in this coupled resonator system by introducing an additional mass, then the symmetry will be broken such that vibration energy, instead of being equally distributed between the two resonators, become confined to one of the resonators. This vibration energy confinement can be experimentally recorded by measuring the individual amplitude of vibration from the two resonators and observing the amplitude ratio. So for this coupled resonator system, these are the equations for the resonant frequency at the out of phase mode and the in phase mode. Similarly, these are the equations for the amplitude ratio obtained from this coupled resonator system when they are operating at its out of phase mode and in phase mode. Now let me explain about this coupled MEMS resonator design. So this is a free floating coupled MEMS resonator anchored at the four corners. And I have designed this MEMS resonator such that it operates in its Lame mode as opposed to the square extensional mode in the previous work. I have chosen the Lame mode because in this mode, the square plate extends in two directions and contracts in other two directions, because of which the volume at this mode will be conserved when the MEMS resonator operates at this mode, and higher quality factors can be obtained when the square plate resonators operate in this mode. Now, to test the sensitivity of the coupled MEMS resonators to the ultrafine particles, an experimental setup was constructed. So this is the experimental setup which I constructed with the help of my peers in the engineering department. And I would like to take this opportunity to thank my peers for helping me to construct this experimental setup and for helping me to carry out this experiment. So shown here is the soot particle generator comprising a burner arrangement. So this is where how the particles will be generated. And the size of the soot particles that are generated can be adjusted by adjusting the flow rate of propane. The particles that are generated will then be passed through an aging chamber, and then they will be connected to the reference instrument, such as the differential mobility analyzer and the condensation particle counter. The soot particle output will also be fed to another differential mobility analyzer for fine tuning the size of the particles, that is 200 nanometer, which will then be fed to the MEMS impactor stage by inertial impaction on the MEMS resonators. The variations in amplitudes of the two individual resonators in the coupled resonator system will then be monitored using a two-channel lock-in amplifier. Since there are two resonators connected together, we are monitoring the amplitude output from the two resonators using a two-channel lock-in amplifier. Now, this experiment here is a forerunner for the work which I have proposed for this CAPE project. So I should mention that these results obtained from this experiment also got published in the special issue of the journal Census and got selected as a cover story out of 328 articles published in that issue of the journal. So these are the soot particles that are deposited onto the sensitive points of the resonator when they are operating at their Lame mode. For the Lame mode, the red points over here are the sensitive points. So the aim of this experiment was to generate 100 nanometer size soot particles and test the sensitivity of the MEMS resonators to the generated particles. If we look at these soot particles in a microscope, these particles just appear as if they are a black dot. But while observing through SEM imaging, we can clearly see the size of the particles and the distribution of the particles on the resonator surface. So this is the size distribution of the 100 nanometer sized particles measured using the differential mobility analyzer, which is the reference instrument. And this graph shows the frequency and amplitude shift of the coupled resonators in response to the soot particles deposited for about 40 minutes on the resonators. So when I was doing this experiment, the frequency peaks didn't appear to shift with increase in particle deposition. So I wasn't sure if the resonator was sensitive at all to the particles deposited. But when the response was zoomed in, so it clearly showed the small shift in frequency and amplitude depending on the mass of the particles deposited. So this red dot over here, the red dotted graph over here shows the response from the resonator 1, and the blue dotted graph over here shows the response from the resonator 2. So considering the amplitude of the resonator 1 and amplitude of the resonator 2, amplitude ratio will be considered as the output metric to determine the mass of the particles that are deposited on the resonators. Then I compared the frequency shift based on the mass of the particles deposited and the amplitude ratio shift based on the mass of particles deposited. So here you can see the amplitude ratio shift increases and the resonant frequency shift decreases. If we compare the sensitivity factors based on frequency shift and amplitude ratio shift, it became very clear that the amplitude ratio output metric provided 3 orders of magnitude improvement when compared to the traditional frequency shift output metric. So the sensitivity of this coupled resonator based on amplitude ratio output metric has been verified for the ultrafine soot particles. Then the Allan deviation graph was plotted to compare the stability of the amplitude ratio and frequency output metrics by monitoring the shift in frequency and amplitude ratio for a 12-hour period. This is to monitor the variations in the amplitude ratio and frequency for long-term measurements. The point of using this Allan deviation plot is also to see what would be the minimum variations in the amplitude ratio and the frequency shift that can be obtained over time. So the minimum of these peaks over here shows that a minimum deviation in the amplitude ratio can be obtained as 0.00577. This then represents the amplitude ratio stability for long-term measurements in the coupled MEMS resonator system. Similarly, the best case frequency stability was obtained as 0.0297 Hertz. And then by combining the previous sensitivity data and this stability data, the input referred stability was calculated. This input referred stability is calculated to obtain the minimum mass that can be sensed based on the frequency shift output metric, which is the traditional method, and the amplitude ratio shift output metric. So while observing the minimum mass that can be estimated based on the frequency shift output metric and the amplitude shift output metric, it was seen that the minimum mass that can be estimated based on frequency shift is 2.16 picogram and amplitude ratio is 367.8 picogram. If you look at this graph, it is also clear that the amplitude ratio stays stable for long-term measurements, whereas the resonant frequency fluctuates, proving that the amplitude ratio output metric is a better one for long-term measurements of these ultrafine particles. And here this graph shows the mass estimated based on the coupled MEMS resonator equations that were calculated, which is then compared with the mass indirectly estimated based on the condensation particle counter, which is used as the reference instrument. There are deviations based on the mass, which is calculated for frequency shift and amplitude ratio shift. And these deviations could be because of the spatial sensitivity issues associated with the MEMS resonator, and can also be because of the non-uniform deposition of the soot particles on the resonator surface. But the input referred stability, which is the minimum mass, which can be estimated based on the frequency shift output metric and the resonant and the amplitude ratio shift output metric, is verified for this experiment. Now, the other important thing to notice in these resonators, when particles get deposited on the resonator surface fills quickly. So if the concentration of the particles is very high, the sensor lifetime will be reduced. That is, we will have to replace these resonators immediately. So one thing what we did is, in order to test the lifetime of these sensors, we tried initially impacting 100 nanometer polystyrene latex particles at higher concentration onto these coupled MEMS resonators for 5 minutes on the first resonator and for the next 5 minutes on the second resonator to see what would happen in the coupled MEMS resonator system. For observing this response, we chose the in-phase mode of operation because the amplitude ratio starts at 1 for the in-phase mode. So what we have observed is when particles were deposited on the first resonator for about 5 minutes, the amplitude ratio, which was initially at 1, tends to diverge based on the mass which is deposited on the resonator. Then when we proceed to deposit mass on the second resonator, the diverged amplitude ratio converges and tends to become 1. So the amplitude ratio starts at 1 and goes back to 1. So this proves the mass balancing capability of the coupled resonator system, by which we can extend the sensor lifetime without having to go for any other wet or dry cleaning techniques by extracting the resonator out of the MEMS impactor stage. So another experiment which we did is testing the sensitivity of these resonators to temperature. So if we look at this graph, when particles were deposited on the first resonator, the amplitude ratio varied, which shows the amplitude ratio output metric is sensitive to the mass deposited on the first resonator. Similarly, when mass was deposited on the second resonator, the amplitude ratio varied again. It also proves that the amplitude ratio shift output metric is sensitive to the mass deposited on the second resonator. But when we changed the temperature or varied the temperature, this amplitude ratio shift output metric stayed constant, which proved that this coupled MEMS resonator system is insensitive to temperature, but highly sensitive to the mass that is deposited on the coupled MEMS resonator system. So this proves the validity of using this coupled MEMS resonator system as a field deployment equipment for long-term measurements of ultrafine particles. So far, we have seen the ability of this coupled MEMS resonator system to exhibit 3 orders of magnitude improvement in sensitivity based on amplitude ratio shift output metric. And we have also seen what is the minimum mass that can be estimated based on the stability measurements obtained from this coupled resonator system. We have also seen the common mode rejection capability, that is insensitivity to the temperature, and mass balancing capability of this coupled MEMS resonator system. So what exactly is the mastery of the MEMS technology in tackling air pollution? To know that, you'll have to wait until the next part of this presentation, which will be in the June event. So thank you for listening.
Thank you, Malar, for this very interesting presentation, and I would like to open the floor to any questions.
I have a question here. It's very interesting. Thank you. One thing wasn't quite clear. How do you do the selectivity of the PM with your sensor? Because you measure the mass, but can you actually distinguish the size of the particle?
Yeah, so in these experiments, we didn't test the selectivity, but then we were focused on the size of the particles, which is the ultrafine and the particle size less than 300 nanometer. But the selectivity of this MEMS resonator to the particles can also be tested if we tend to look at the initial frequency response, which can be obtained from this coupled MEMS resonator system to different particles. So that has not been shown anywhere, but that would show you the difference for different particles. So based on that, one could say which type of particles are there on the coupled MEMS resonator system.
Okay, thank you.
Yeah, I have shown the long-term measurements based on the particle deposition. But as you asked to see the selectivity, we will need to look at carefully the initial measurements obtained from the coupled MEMS resonator system to consider how it is selective to different types of particles.
Thank you. Any more questions, please? If not, I would like to thank Malar. Thank you very much. And we look forward to part 2 in June, to your final presentation.
Sure.
Thank you. So this was our last talk, and I found all presentations are very interesting. So I would like to also mention that we have issued yesterday a new call for CAPA 2021, and the deadline for the applications is on 19th of March So we look forward to receive more applications and see more interesting projects.
Thank you very much. I just want to say the thanks to everybody for the excellent work and also very interesting presentation. And I think we will put your presentation onto the website of the CAPE, and Denisa also start a YouTube channel. So probably we can put it there as well.
Yes, we will do so.
Okay.
So thank you very much, everyone. And yeah, we look forward to seeing you in the next CAPE event in June. We will circulate again the invitations. Thank you. Bye-bye, everyone.